Hello, this is Buono. Today I'd like to talk about the difference between DC and AC. Earlier in the episode on circuit symbols, the words DC and AC came up as names only. This time we'll look head on at what actually makes the two different. And don't worry, we won't use any difficult math. The key to telling them apart is just one thing: the direction the electricity flows. In fact, this difference is right next to us in daily life. The battery in your phone and the outlet on the wall. They look like the same electricity, yet the way they flow is completely different. Once you see what's really going on, you'll even understand why the charger you use without thinking is necessary. It's the very first distinction worth getting down when you learn about electricity. By the time this video is over, you'll be able to explain in your own words what makes DC and AC different, using the shape of the waveform and everyday examples like batteries and outlets. You'll hardly need any prior knowledge, so please watch to the end. Let's start with DC. It's short for direct current, so it's also called DC. In a word, direct current is a way of flowing in which the direction of the current, the plus and minus of the voltage, never changes over time and stays constant. If it flows to the right, it keeps going right, always the same direction. Think of it as a one-way river that always flows in the same direction. Even if the force of the water gets a little stronger or weaker along the way, the direction itself never reverses. The direction doesn't change is the single biggest feature of DC. Let's see this on a graph with time on the horizontal axis and the size of the current on the vertical axis, a waveform. The representative form of DC is, as you can see, a flat horizontal line, graph number 1 on top. Since neither direction nor magnitude changes, it's a single flat line. What matters here is that what decides whether something is DC is not magnitude but direction. Look at graph number 2 below. Here the line moves up and down, so the magnitude wobbles. Even so, it never drops below 0. In other words, the direction stays the same the whole time. So this too is genuine DC. Even if the magnitude changes a bit, as long as the direction doesn't change, it's DC. Keep that in mind. Next is AC. It's short for alternating current, so it's also called AC. AC is the exact opposite of DC. It's a way of flowing in which the direction of the current, the plus and minus of the voltage, goes back and forth, reversing periodically. It flows right, then the next moment left. It repeats this rhythmically and regularly. For this one, think of ocean waves. They roll in and roll out, roll in and roll out, changing direction back and forth in the same rhythm, repeating. That's the image of AC. Now let's compare it on the same kind of waveform. Whereas DC was a single flat line, the representative form of AC is a wave that swings smoothly up and down around 0 in the middle. When it's above and when it's below, the direction of the electricity has flipped. DC is a straight line, AC is a swinging wave. Look at this difference in shape and you can tell the two apart at a glance. That said, from a wave graph alone, the direction reverses may be hard to picture. So let's look at it with a more familiar image. Here I've set up two identical circuits, each with a small light bulb. The only difference is which way the battery faces. First, the circuit on the left. When the plus and minus of the battery face this way, the current flows clockwise, like the arrow, and the bulb lights up. This is the time when the wave is bulging upward. Next, the circuit on the right. After a little time passes, as if the battery had flipped the other way, the direction that pushes the electricity reverses. The current reverses too, and now it runs counterclockwise. Through the same bulb, the electricity now flows the opposite way. This is the time when the wave is bulging downward. There isn't really a battery inside the outlet that flips its direction, but it helps to picture the direction that pushes the electricity switching right, left at tremendous speed. AC is electricity that keeps repeating this clockwise and counterclockwise, and clockwise plus counterclockwise make one set. That's one cycle of the wave. This set repeats as many as 50 to 60 times every second. It's so fast that the bulb just looks like it's lit normally, while we never notice the direction is changing. Next, let's see where these two live around us. First, a familiar example of DC is the battery. Dry cells and the batteries inside smartphones are all DC. That's why a battery has its plus and minus directions clearly fixed. On the other hand, a familiar example of AC is the household outlet. The electricity coming from the wall outlet is AC. Unlike a battery, whose plus and minus directions are fixed, the electricity from the outlet arrives while its direction keeps reversing periodically. Now, some of you might have found this a little puzzling. If the outlet is AC, how do phones and computers run? In fact, many of the electronic devices we use run on DC inside. That's where the AC adapter comes in. The charger for your phone or laptop is exactly this. An AC adapter is, so to speak, a currency exchange from AC to DC. It takes in the outlet's AC and exchanges it for the DC the device wants before handing it over to the device. Around us, both AC and DC exist, and they're used by converting between them like this. Here's a surprising bit of trivia. Actually, the AC from household outlets differs between the east and the west of Japan. Eastern Japan is 50 Hz, Western Japan is 60 Hz. This quantity that tells how many times the wave repeats per second is called frequency, and its unit is Hz. Picture how many times a metronome ticks per second. At 50 Hz, for example, that wave repeats 50 times every second. For today, it's enough to think AC also has these differences in the speed of the wave. So why did East and West split? This goes all the way back to the Meiji era. In 1895, the Tokyo Power Company imported German generators, and a little later, around 1897, the Osaka Power Company imported American ones. The German ones were 50 Hz, the American ones 60 Hz. Each spread across its region and remains today. It's a historical story of how the difference in where they were imported from simply settled in as each region's standard. The boundary runs roughly from Itoigawa in Niigata Prefecture to the Fujikawa area in Shizuoka Prefecture, and to share electricity between east and west, you even need dedicated facilities to convert the frequency. Within a single country, the outlet frequency is split into two kinds. That's actually quite rare even by world standards. Now, a quick check to test your understanding. Again, 3 questions that trip you up if your memory is fuzzy. Give them a little thought. Question 1. The magnitude of the current changes, but the direction stays the same the whole time. Which of the following is this kind of electricity? 1. DC, 2. AC, 3. Neither. Question 2. The difference between AC and DC is whether the magnitude of the electricity changes. Is this true or false? Question 3. The AC adapter, familiar from phone chargers. Which of these is the job it does? 1. It converts AC into DC. 2. It converts DC into AC. Have you settled on your answers? Let's check them on the next page. Alright, let's check the answers. The answer to question 1 is number 1, DC. What decides whether something is DC is not magnitude but direction, remember? Even if the magnitude changes a bit, if the direction stays the same, it's DC. The answer to question 2 is false. The difference between AC and DC is not whether the magnitude changes, the decider is direction. AC is what reverses direction periodically, DC is what stays constant. The answer to question 3 is number 1. The AC adapter is a currency exchange from AC to DC that swaps the outlet's AC for the DC the device wants. How many did you get? Go back and review the ones you missed. So today we've explained the difference between DC and AC. First, electricity had 2 ways of flowing. DC, whose direction is always constant, and AC, whose direction reverses periodically in their representative waveforms. DC is a single straight line, and AC is a swinging wave. Just by looking at the shape, you can tell them apart at a glance. And here's the through line of today. What comes from the wall outlet is AC. But electronic devices like phones and computers run on DC inside. The ways of flowing don't match. That's exactly why the AC adapter that connects them converts AC into DC to bridge the gap. The outlet is AC, the device is DC, so we convert. Today's story all connects along this single thread. From now on, remember electricity, which has these two faces, DC and AC, through the shape of the waveform and examples like batteries and outlets. Keep it in a corner of your mind. That's it for today. Thanks for watching.